Imagine running a complex, three-dimensional topographic simulation, only to watch the entire mesh instantly flatten into a featureless plane. That failure happens because assembling the baseline Laplace equation naturally results in a right-hand side vector of exactly 0. If we run the calculation as is, the math perfectly balances out, giving us a completely zeroed vector for every unknown node. In numerical methods, this self-canceling dead end is known as the trivial solution. Physically, a trivial solution means your engineering model predicts absolutely nothing happening. No heat flow, no stress gradient, no movement whatsoever within the domain. To get actual results, we have to find a way to force non-zero values into this closed, perfectly balanced system. The global matrix is mathematically complete, but it remains physically useless until we forcefully inject the outside environment's reality into our equations. That outside reality comes in the form of boundary conditions, the fixed, known values strictly existing at the outer edges of our physical model. To use them, our algorithm has to physically separate these established boundary values from the unknown internal nodes we actually want to solve for. The goal is to extract those known variables and shift them across the equal sign, entirely replacing that inert zero vector. The specific algebraic technique we use to execute this extraction is called matrix partitioning. This partitioning process takes passive physical constraints and turns them into an active forcing vector that drives the physics of the entire simulation. Let's build a proof of concept using a 2D element with 4 corner nodes. We enforce boundary conditions on the left, setting nodes 1 and 2 as known values f1 and f2. Nodes 3 and 4 remain unknown targets phi3 and phi4. A standard finite element assembly combines all 4 of these nodes into one rigid matrix equation. In this combined state, solving the system is mathematically impossible. The known constants and the unknown variables are locked together within the exact same vector. To solve this basic 4-node model, we have to algebraically tear the matrix equation apart along the precise boundary lines we just drew. This is the raw, assembled 4x4 Laplace matrix for our single element, completely unprocessed. Notice the column vector on the left. It traps the known f values and the unknown phi values in a single stack. We need to separate them by conceptually grouping the matrix rows associated with the known boundaries and the rows tied to the unknown interior. Applying linear algebra, we bisect this system horizontally, splitting it into 2 independent equation sets. Here is the direct result of that split: 2 distinct submatrices broken out from the original 4x4 block. The upper equation set is now entirely dependent on our known boundary values. The lower equation set is what matters. It governs the strict mathematical relationship between the fixed boundary and the unknown internal nodes. This second block of equations is our escape route from the trivial solution. The physical boundary we placed on nodes 1 and 2 is now perfectly mirrored by the algebraic separation of the equations, finally isolating the unknowns. Let's look closely at that second set of equations generated by our matrix split. Our immediate mathematical goal is to isolate the phi variables entirely on the left side. We start by multiplying the isolated boundary submatrix by the f vector. Then we execute the critical shift. We move that entire product block across the equal sign, pushing it to the right-hand side. This gives us our final resolved algebraic state at the bottom. The unknown variables now equal the inverted stiffness submatrix, multiplied by the now active boundary terms. By shifting the knowns, we replace those trivial zeros with a forcing vector derived from the boundary values. Standard matrix inversion is now possible. Watch what happens as we take that single mathematical element and rapidly multiply it into a dense, sprawling continuum. The exact partitioning logic we just derived for a 4-node rectangle scales automatically to handle stiffness matrices containing thousands of elements. To prove this algorithm at scale, we use a standard computational benchmark known as the cavity flow problem. The parameters are strict. 3 outer boundaries of our domain are forced to absolute 0, while the top edge is held at a constant unit value of 1. If we skipped the matrix partitioning step, the 3 zero boundaries would dictate the entire system, pulling every calculation down to a trivial 0 vector. This plot shows the partitioned cavity flow output. Notice the 0 constraints along the vertical edges and x-axis. The simulation draws energy from the single unit boundary on top. Concentric gradients curve smoothly from that active boundary into the base. This continuous scalar field represents the calculated values of all the internal nodes that were previously unknown. Seeing these gradients proves that our single boundary constraint successfully propagated through the internal algebraic equations. The cavity flow contours prove matrix partitioning works. It turns an inert, self-canceling global matrix into a solvable, physically meaningful simulation.